This is Rosen, section 5.3 on recursive relations and structural induction. And here we introduce the concept of structural induction. We can prove properties about recursively defined sets by leveraging their definitions. If we show something holds for the elements in the basis step, that's the start, and then if we can show that whatever statement that we're trying to prove is true for each of the elements used to construct the new elements using the recursive step, then the result will hold for new elements, and then therefore all elements in the set. Because that's the only elements in the set is those that are created by the basis step and recursive step. And this follows from mathematical induction on n, where n is the number of applications of the recursive step. All right, let's look at an example. First, we'll talk about a recursive set called the set of full binary trees. And the way we build these up is we start with a single vertex R. And then in recursive step, we say that if there are two trees in the set, we can create a new tree by establishing a new root R. And then we connect R to the roots of tree 1 and tree 2. Tree 1 to the left and tree 2 to the right. Here's the first three applications, or the basis step in the first two applications of the recursive rule. So the basis step gives us a single vertex, which is a root. In step 1, we can create a new root, and then we can append to the left and right a single root because that's all that's in the set. But now in the second application, we get a new root, and then we can append any binary trees that are in the set from prior applications of the algorithm. So here's a single root, here's a root with two branches, and so forth. And so if we wanted to create a tree from step 3, we would create a new root R, and then over here I would put T1, over here I'd put T2, and we'll just say T1 is that, and T2 is that. And that would be a tree created in step 3. All right, so we've got some functions that we can define for full binary trees, and they're defined recursively as well. We'll talk about the height of a full binary tree. It's defined recursively this way. The height of a full binary tree consisting just of a root is 0. Okay. And then the recursive step, if I have T1 and T2 in my set, and we create a new tree, T, with T1 and T2, then it has height 1 plus the maximum height of T1 and T2, maximum of those heights. So here's a new tree we're creating from two trees that were already in there. Here's R, here's T1, here's T2. The height of T2 equals 1. Height of T1 equals 0. And we'll call this T. Height of T equals 1 plus 1 equals 2. Okay, the next one's more straightforward. It's the number of vertices in a full binary tree. And the basis step with just R, a single root, the number of vertices is just 1. And the recursive step, by combining T1 and T2 into a new tree, then I'll get all the vertices from T1 plus all the vertices from T2 plus the new root to give me the total number of vertices in the new tree. Okay. All right, so now Here is the theorem we want to prove using structural induction on how this tree is built up. I want to prove that the number of vertices in a tree is less than or equal to 2 raised to the power of the height plus 1 minus 1. And we'll prove it for the basis step using structural induction. And in the basis step, we only have a single root, and the number of vertices is 1, the height is 0, and we'll check to see if our theorem holds. Number of vertices is 1, it's less than or equal to 2 to the 0 plus 1 minus 1, which is 1, so everything checks out on the basis step. All right, let's try the recursive step. We're going to assume that the theorem holds for trees already in my set. Call those T1 and T2. And then we're going to see if the relationship holds to a tree created with those in the next recursive step. So now we're going to create T from T1 and T2. That is, we're going to have a root with T1 over here and T2 over here. And the number of vertices, as we had said before, is 1 plus the number of vertices in T1 plus the number of vertices in T2. But we can apply the inductive hypothesis to these values here in a greater than sense. So that's going to be, NT is going to be less than 1 plus 2 raised to the height of T1 plus 1 minus 1 plus 2 raised to the height of T2 plus 1 all minus 1. That's again by the inductive hypothesis, since T1 and T2 were already in my set. Okay, this 1 will cancel that one, leaving me with minus 1 to keep track of. And then I'm going to consider another inequality. One of these is potentially bigger than the other, so their sum will be less than or equal to twice the max of these two values. So twice the max of these two values, then minus 1. And then since the max of 2 to the x and 2 to the y is 2 to the max of x and y, I can rewrite this as 2 equals 2 times 2 to the max, the height of tree 1, height of tree 2 plus 1. Well, that is precisely the definition of the height of tree T. So I'll replace that with h of t. And then if I bring the 1 from this coefficient of 2 inside, I get nt is less than or equal to 2 to the ht plus 1, all of that minus 1, which is exactly what we were trying to prove. And we did that using structural induction, leveraging the definition of our set of binary trees.